Imagine you're new to the city but hungry and looking for restaurants to eat, and you suddenly bump into two. One with a perfect 5-star rating but only 19 reviews, and the other with 4.4 stars but 500 reviews. Which one do you go for?
This video is about the most fundamental ideas in all of reinforcement learning. How does an agent know whether to trust what the data deems convincing right now versus to explore and try something new instead?
This video is part 1 in a series on AlphaZero, the AI that use principles of reinforcement learning, neural networks, and this kind of mathematics to build a model that defeated the world's strongest chess players and agents only through self play and no human instructions. Let's say instead of ratings, you were given rewards every time you were to make such a decision. Now, if you make one decision multiple times, you won't get the same reward again and again. That variable would be a random variable. Let's say that is x of I, and the average of that variable is x bar. Now, we really want to quantify how far can x bar stray away from its true mean. So, we really want to find out the probability that the minimum deviation is at least t. Now, how do we figure this out? Let's say that x is centered around 0, meaning that the expectation of that is 0, but the range is a to b. Now, how do we make observations about this? How do we make observations about this probability, about how likely it is to stray away? And where does a bound like this even come from? So notice something here. For any non-negative random variable y in this case is x minus u bar. If you were to compute the integral y f of y from 0 to infinity, that would give us the expectation of that variable. Now we can use the inequality that this will be always greater than some integral t to infinity of the same integrand. And since we know that y is always greater than t under this region, we can say that y f of y is greater than t f of y. And thus we get this inequality. So by a simple logical argument, we've derived this relationship between the probability of y being greater than t and the expectation of y. This is known as the Markov's inequality, and this will be a fundamental tool in our following derivations. In our random case, x can be any variable. It can also be negative. But since Markov only needs a non-negative variable from our derivation, we exponentiate this variable and apply the Markov's inequality on e to the power lambda x. Now notice that this is always positive, and we get this inequality for expectation of e to the power lambda x. Now our job is to figure out the dynamics of e to the power lambda x and its expectation. Well, the very first thing that we can notice about it is that it's a convex function, meaning that any secant of this curve lies above it. So if you take any 2 points with x coordinates a and b, because that's the range of x, and draw a line through them, this line will always lie above this curve. Express that as an equation and take expectation on both sides, and since we use the fact that expectation of x is 0, we get this. Now we do a clean substitution where we put minus a by b minus a as p, so that we get a clean value range for p and we get a nice function. Now how do we find the upper bound of this function? First we take the log on both sides and notice something. The function on the right is noted by psi of lambda, and we put d as b minus a temporarily. Now the right hand side is defined as g of lambda, and we really want to find out the maxima of g of lambda. So notice one fact: g of 0 is equal to 0, and g, the derivative of g with respect to lambda, gives us 0 at 0. Now we can expand out the Taylor series of g of lambda near 0 as this, where the first two entries are going to be 0. So we found out g of lambda equals the second derivative times lambda square by 2. So how can we find out that? We use some standard calculus and we take the first derivative and equate it to 0. You really want to maximize q1 minus q, where q is belonging to 0 to 1 range. And after taking the derivative, we get q at 1 equal at half as the maximum quantity. So we put that back into our expression, and the second derivative of g is maximized at lambda equals 1/2. Plug that back into the equation and we finally found out the maxima for g of lambda, which is lambda squared d squared by 8. Plugging this back into our psi and g inequality, we get this lemma. Also known as Hoeffding's lemma, this is exactly what we'll be using in the future derivation. Now notice that we are not just dealing with one example here. We're really dealing with multiple samples, and we really want the probability distribution of the actual mean being away from the computed mean by some epsilon. What's the probability of that? Now this is where we use the Markov's inequality that we have derived. So we plug it back into the expression. Now since x bar is a summation, we turned it into a product because it's an exponent, and now we apply the lemma back. Finally, we get this result of the probability of the mean being away from the true mean by at least epsilon as exponential. So we now have the maximum probability of being wrong, and you can see that it collapses exponentially fast with epsilon. So instead of asking how big the error epsilon can be, let's ask how big can the probability be? What's the maximum probability? Let's set that equal to delta, and let's find out epsilon in terms of delta. Then we plug this delta or epsilon back into the expression for the means, and now we have the confidence interval with probability at least 1 minus delta that the mean is going to be x bar plus epsilon. So we now have an upper confidence bound. Now for our purposes, what do we set this delta as? Since we want the delta or probability of being wrong to decrease with the number of times you're visiting that question, you can set it inversely proportional to n or capital N. But we can't set it to 1 by n since delta is a probability and its summation would be infinite. So we set it equal to 1 by n to the power 4. Plug this into our equation and we finally get a upper confidence bound, where n, small n, refers to the number of times you visited that state, and capital N is the total number of times that we are equating this question. So finally, we have achieved this metric. Let's unpack what it really says. X bar I is really telling us what we know right now. It's the average rewards or outcomes that we know. And this term is kind of can be interpreted as an exploration bonus. It uses the fact that we don't know something, and it gives bonuses to the options visited less number of times. Now, do you remember the first example from this video? Let's actually compute the upper confidence bound for both of these restaurants. The first one had a 4.4-star rating with 500 reviews, and the second one had a 5-star rating with 19 reviews. So the UCB score for our second restaurant comes out to be more than the first one in this example. So what UCB deems is that even though there's uncertainty in the second example, there's still kind of a meaningful uncertainty. Like even though there's less number of reviews, the fact that there's still 5-star reviews on it comparatively gives it the edge. So if you're someone who's exploring the restaurant or exploring the restaurants in your city, that's the better way to go. This kind of reasoning holds much more weight when you're trying to do sequential decisions, especially in games like chess and Go. This is exactly what we'll be deriving, constructing, and coding from absolute scratch in the following two videos, so stay tuned for more.